So good morning students, welcome back. Today we will discuss the topic moving coil galvanometer M.C.G. That is one of the most important topic for board's point of view. So let's start first of all definition. Okay, we are having the topic moving coil galvanometer. Okay, what is moving coil galvanometer? A device that is used to find very small amount of current is said to be moving coil galvanometer. Okay, suppose you are having 2 ampere current, 5 ampere current, okay, 7 ampere current. If you want to detect the current of 2 ampere, 5 ampere, 7 ampere, we can measure by ordinary or simple galvanometer. Okay, by a simple galvanometer. Okay, this type of current 2 ampere, 5 ampere, 1 ampere, 3 ampere, 7 ampere. But suppose if the amount of current is 0.001 ampere, that small amount of current, okay, so that we cannot measure using by this galvanometer, ordinary galvanometer. For measuring such small amount of current, we have to use the device moving coil galvanometer. Actually, this moving coil galvanometer is a very sensitive device. It gives the large deflection for very small amount of current. So basically, it should be clear that a device that is used to find very small amount of current, that is used to find the current, is said to be moving coil galvanometer. Okay. Now students, its principle. It is based on the principle that whenever a rectangular coil placed in magnetic field, then it experiences torque. Okay. Whenever a rectangular coil or any other coil placed in magnetic field, it experiences torque, and that torque provide that coil the free rotation. Okay, on that principle it is based. Now students, we'll discuss about construction. That is most important. So let's start the construction part. Look students, as you can see, very first thing, it consists of a strong cylindrical permanent magnet, north pole and south pole. This is the cylindrical, this is made some curve like, okay, this is strong magnet, north and south, that generate strong magnetic field. Okay, so the question arises, why we use this curved magnet, cylindrical magnet? Actually, that produce radial magnetic field. Okay, in this condition, in this type of a magnet, all the field line move towards, all the magnetic field line move towards the center. In such condition, such type of magnetic field is said to be radial magnetic field. So again the question arises, why we require radial magnetic field? Actually, this radial magnetic, due to this radial magnetic field, okay, all the magnetic field is focused at the center coil, as well as, okay, the magnetic field remains parallel. Radial magnetic field remains parallel for all of the position of the coil. Understood? Okay, it remains parallel for any condition of the coil when it rotates. Okay, that's why we require radial magnetic field. Now the next thing, first north and south pole, strong cylindrical magnet, permanent magnet, then radial magnetic field. Okay, and then next we are the most important, this is coil. This coil is made by soft iron core on which copper wire wound. Okay, so this is the coil, and this is that you see this type of line. Okay, this is copper turns bound on that coil. I will give you example. Suppose this is a cylindrical coil. Okay, and when we wound copper wire on it like this, look, so it looks like, see, in front of it you can see like this. Okay, look students, it will looks like this. Look at it, is looks like this. It is looks like, so this is suppose cylindrical coil, okay, on which we wound copper wire like this, okay, in this helical form. So it will looks like this. This is coil and this is copper turn on it. Understood students? So now students, and this coil at the bottom, from the lower side, it is connected with a spring. Now what is the function of that spring? that spring provides free rotation to the coil. Okay. Now students, this coil is connected with a pointer. This pointer is made by light material like aluminum, and that pointer is connected with this scale on which we can find the deflection of the current. Okay. So this is basic construction. One important point. This is top view. When you see the moving galvanometer from the top, okay, suppose this is moving galvanometer. When we see from the top, okay, it looks like this, but this is the front view. Okay, that is easier to understand. I will explain that also. Look, students, this is coil. So this is our coil. Copper wire. This is copper tongues. Okay, wound on it. North and south pole. North and south pole. Spring. Now look, this diagram can easily explain. This is the coil and a spring is connected. So spring is connected like with this lower portion. It provides rotation, and upper part of a spring is connected with a mirror. What is the use of mirror? At the last of that, this topic we'll discuss also, but I will tell you, with the help of this mirror and lamp and scale, we can find the angle of deflection phi of this coil. When the coil rotates, it rotates with some angle. That is called angle of deflection. Later on we'll discuss that angle we can find using this mirror and lamp and scale method. Later on, at last we'll discuss. Okay. And the most important thing, this wire, this spring and this wire is made by phosphor bronze element. Why we use phosphor bronze element? Because that is a good conductor as well as having the property of elasticity. So it can easily twist with the rotation of coil. This wire is made by phosphor bronze. That is an important point. And at last, the wire is connected, pivoted, it is fixed with torsion head. What is the meaning of torsion head? It is just like a ball bearing. It provides free rotation. Due to this torsional head, this coil can rotate about its own axis like this. Okay. Suppose like see, this head can rotate like this. Why? Because this having the torsion system look like this. Okay. Upper end is connected with positive terminals, while lower end is connected with negative terminals of the cell or battery. Okay, that is the basics construction of the moving galvanometer. This is top view and that is the front view. Now students, we'll discuss the working part of moving coil galvanometer. Look students, as soon as when you flow the current with the help of terminals by using battery or cell, when the current will flow in this coil, in this rectangle coil, we know students, whenever a rectangular coil having current and place in magnetic field, so whenever a current carrying coil placed in magnetic field, it experiences torque. Okay, that is called deflecting torque, and given by the formula NIAB. Actually, torque is NIAB sine theta. Okay. Actually, we are using radial magnetic field and coil. And what is the direction of area of coil? That is normal to the surface. So theta is 90. On sine 90 will be what? 1. That's why we are using only NIAB. Okay. Look students, where N is the number of turns of this coil, I area of here, N is number of turns of the coil, I current in the coil, A area of the coil, and B is the magnetic field around the coil. This is called deflecting torque. Due to this different torque, okay, it gets deflection, and the torque is directly proportional to the angle of deflection. Obvious, when current is more, when the amount of current is more, it deflects with large angle. Okay, when the moment of force torque is more, in that condition angle will be more, it will deflect with more angle. So torque is directly proportional to angle of deflection. Obvious, more torque will provide more deflection. Due to the property of elasticity, okay, this coil will get restoring torque. This is called restoring torque. Torque is proportional to phi, and whenever we remove this proportion, we always use equivalent constant. Here I am using the constant K. K is called torsion constant because you are having a torsion system. That's why it is called torsion constant. And phi is called angle of deflection. It is that angle with which the coil rotates. And torque is called restoring torque. This torque is set up due to the elasticity property of this spring. On balancing state, deflecting torque will equals to restoring torque. Okay. So look, students, you can copy this. You can take a screenshot. I'm going to remove this. Just remember NIAB and K phi. So from equation first and second, when left hand side equal, right hand will also equal. So in balancing state, what happens? In balancing state, NIAB will equals to K phi. Okay, K phi. Okay. Now students, NAB by K. NAB by K, and that is phi upon I. Look at students. So deflection for unit current of galvanometer is NAB upon K, where N is number of turns, A is area of coil, B magnetic field, K is torsion constant, I is current, and phi angle of deflection. Deflection for per unit current is always remains constant. It is represented by G. That is called constant. That is called constant for galvanometer. Deflection. Okay, deflection for per unit current. When you flow the current, this pointer gives the large deflection. So deflection of per unit current is said to be constant for galvanometer, represented by G, and having formula NAB upon K. Okay. But important thing, students, how can you find phi, angle of deflection? That we can find by this mirror. By using lamp scale method, we can get the value of phi. Okay, and if we are given this factor, we can find the amount of current I. In this way, we can calculate the current using a moving coil galvanometer. Understood, students? And now, students, sensitivity of galvanometer. Actually, moving coil galvanometer is a more sensitive device for very small amount of current. So first we'll discuss current sensitivity. Deflection for per unit current in moving coil galvanometer is called current sensitivity. Deflection for per unit current, it means for very small amount of current, the galvanometer will give the large deflection. And you know what is the value of I? We found in moving coil galvanometer, K phi upon NAB. When you put here K phi upon NAB, phi to phi cancel out and it become NB upon K. So that is the formula of current sensitivity. Depends on number of turns, magnetic field, area, and torsion constant. While voltage sensitivity, deflection for per unit potential is called voltage sensitivity. For per unit voltage is called voltage sensitivity. We know by Ohm's law what is V? IR, and this value K phi upon NB when we put here will get NB upon KR. This is a formula of voltage sensitivity. So we can get the relation Vs as it is and V upon K, that is Is, and that is R. So that is the relation between current sensitivity and voltage sensitivity. V is equals to Is upon R. Is is current sensitivity, Vs is voltage sensitivity, and R is resistance.